We introduced 3D SSR, 3D Subscene Retrieval. With increasing number of complex reconstructed 3D scenes, it is important to be able to retrieve subscenes of interest. Our goal is to retrieve 3D subscenes with similar geometry and object arrangements. The retrieved results can be used for downstream applications such as 3D scene editing or scene generation. Contribution 1. We introduce the task of 3D Subscene Retrieval, 3D SSR. Contribution 2. We tackle 3D SSR using our self-supervised point cloud encoder point crop that outperforms supervised and prior self-supervised paradigms. Input query. A user provides a query queue by specifying a set of axis-aligned bounding boxes. The query consists of an object of interest, couch in purple box, and a set of context objects, chair and side table in blue boxes. For each scene in the database, we find its subscene that best matches Q. Retrieval. We assume the 3D scenes in a database come with axis-aligned bounding boxes, but object categories are not provided. We define subscene similarity based on the intrinsic and extrinsic properties of the 3D object within each box. For intrinsic similarity, we use cosine similarity of codes derived from a trained encoder. For extrinsic similarity, we compute the geometric overlap between the query and target boxes in the world coordinate. S is the 3D subscene from T that best matches Q. Ranking. We rank the retrieved 3D subscenes from most to least similar based on the number of matches and a correspondence quality score. We apply 3D subscene retrieval on the Matterport 3D dataset. Matterport 3D consists of 2,195 rooms with median number of 20 objects per room. To create train, val, and test data, we use the 3D object inside each axis-aligned bounding box in Matterport 3D. Input. We sample a point cloud from the mesh inside each box proportional to the area of the mesh triangles. We take global and local crops of the input point cloud and apply self-distillation training. All crops are fed to the student while the teacher is only given the global crops. We use the same architecture for the student and teacher networks. In particular, we build a point transformer followed by a global average pooling across the 3D points and a projection module. To avoid collapse, we apply centering on the output of the teacher. To update the parameters of the student, we find the cross entropy of the student's output relative to the teacher's output. We update the parameters of the teacher as an exponential moving average of the student's parameters. The trained teacher without the projection module is our encoder for the 3D subscene retrieval task. Each scene is displayed as a pair of top-down images. The top left image shows the entire scene, and the bottom left is the zoomed-in view of the subscene. The query and its corresponding object are in purple. All other context objects are colored according to their category. The subscenes that best match the query in terms of geometric and object arrangement similarity are ours at ranks 2 and 3. Our model retrieves a corresponding chair at ranks 2 and 3 and a corresponding cushion at ranks 1 and 2. The retrieved chair at rank 2 is geometrically very similar to the query chair in purple. The alternative self-supervised model cannot find any correct matches at rank 1, 2, or 3. We train the same point cloud encoder using our point crop versus its supervised version that utilizes category labels. Our result from rank 1 seems to be the best matching subscene. Table, lamp, and cushion are all matching. Please see the paper and the supplementary material for more qualitative and quantitative evaluations comparing our model to baselines and prior work. Thank you.